Hello everyone, welcome back to a new session, Computer Science 2 for summer 2022. Today we are at chapter 17, Standard Template Library. I sent you an announcement for project 4 that it has been posted, and also homework 7, it has been posted. Homework 7 is due 1 week, project 4 is due the end of the semester. So as usual, I have the book in front of me. It's open on chapter 17, page 1029. So the standard template library. What is the standard template library? The standard template library is an extensive collection. If I go to Visual Studio, the standard template library are basically all those libraries that are provided to you by the language. Vector, um, uh, map, set, linked list. That's what you are gonna learn today. Those libraries are templates, just like you learned about templates. A template is a method or a class that can be or can provide you the ability to carry or contain or deal with any data type, whether it's a primitive data type, meaning it's a data type that is provided by the language, or your own defined data types. Similar to vector, now that you know about vector, vector is a template class. So it's provided by the language, it's template class, it can carry any data type. So the standard template library, one of those libraries is a vector. There are a bunch of other libraries that we're going to learn about today. But before we move on, you need to know about 3 terms. You need to know what is a container. You need to know what is an iterator. And then you need to know what is algorithm in general. These 3 are umbrellas that are provided by those template libraries. So what is a container? A container is a class template. It's a class for objects that can store and organize data. An iterator is a class template that behaves like pointers. So it's a class template for objects as well that behave like pointers and are used to access the individual items in a container. An algorithm is a function template. So you have now 2 class templates, function template that perform tasks or various operations on elements of the containers. So again, a container, that's a class template similar to vector for objects that can store and organize data. A vector, you create a vector, you say, I want a vector of integers, and then you start adding integers to that container. You start removing integers from that container. You can iterate, you can access, display, edit, etc. An iterator is a pointer to that container, or not to that container as a whole, but to individual items of that container. So in order to access an item in a container, in a template class, you need an iterator, and we're going to see how we can use it. An algorithm is also provided by the language, and basically it's a bunch or a few of template functions that can operate on those containers. For example, sorting. there is a provided algorithm by the language that is called sort, std, : sort. You give it the beginning of the vector, you give it the end of the vector as iterators. So it takes 2 pointers, one that points at the beginning and one that points at the end of the vector, and it's gonna sort it for you. So that std : sort is a template function that can take any data type. It can take a container of any data type and it will perform that sorting task on that container. So these three things that you need to know before we move on. Now, if we want to break it down, for containers, there are two types. You have sequential and you have associative. Sequential means sequential containers. Associative containers. Sequential means they store the elements or they store their own elements sequentially in memory. For example, if I want to bring up Paint, if this is my memory, the pool of memory in my system, and it has slots, just like you already know now. Let's say this address is 10. So this is 11, 12, 14, 16, 18, 20, etc. An associative container means in memory, the elements are sequential in memory. Means if the first item is at address 16, then the next item is for sure at the next slot. The next item is on the next slot. So all the container is in one block of memory, sequentially. Sequential in memory, just like arrays. Remember in arrays, you tell the compiler or the program, I need my array to be new int 10, meaning give me 10 slots for integers. Those 10 slots are sequential in memory. Sequential meaning the first item would be here, then the next item is on the following address. The next item is on the following address, so on so forth until you reach item number 10. So sequential containers means they are continuous in memory. On the other hand, for example, in blue or purple, you have associative containers. Associative containers means they carry a lot of items, but those items are not sequential in memory. For example, let's say I have my container that has 1, 10, 100, 15, 35, 45. Let's say this is my associative container, and soon we're gonna break which is which container is associative and which containers are sequential. Vector, for example, is sequential. Arrays are sequential. But a quick example for associative containers means it's not necessarily that those are in one block of memory. You might have 1 here, then you might have the 10 here, then you might have the 100 here, then you might have the 15 here, 35, 45. So they aren't necessarily in one block of memory. Then the container will manage how to go from first item to second. Sorry, the second is 10. The program or the container will manage how to go from the first item to the second item to the third item to the fourth item to the fifth item and then to the last item. That's up to the container, but the concept is they are not sequential in memory. So what containers are sequential and what containers excuse me. So sequential containers are arrays, as I explained, vectors, what's called list, which is linked. Oh no, not linked list. List is a doubly linked list. So let's not confuse you for now. These are sequential. Then you have associative. Associative would be a map, set, linked list, linked list. Now I'm gonna separate them because in map and sets you have different types. You have multi map, sorry. You have ordered map, you have unordered map, and then you have unordered multi maps. Maps, when we just say it's a map, we mean it's ordered map, and we're gonna explain it. Similar to maps, sets, we have multi-sets, we have ordered sets, we have unordered sets, and then we have unordered multi-sets. Multi-set and unordered maps. With linked lists, we have three types. We have forward lists. We have doubly lists. And finally, we have circular lists. Now, when it comes to containers, those, as we mentioned earlier, those are classes. And every class has member functions. Remember, they have functions inside them that you can call. For example, in vector, you can call pushback. This pushback function, as an example, you as user of that class, you did not implement pushback. Pushback was provided to you. So that class, that template class, had this member function implemented in it and provided for you to be used by you. Similar to pushback, we have a lot other methods specific to vector. We have other functions specific to array. We have functions specific to maps. Every or each one of these template classes have their own set of functions. However, maybe 75% of the functions are common between all STL. STL means the standard template libraries. So all containers share about 75% of the functions. The same functions are everywhere in any container that you use. Any container that you use, you're gonna have 75% of the functions common. For example, function called size. The size function, when you call vector on your instance, when you create an instance of vector, you can call pushback to add an item to it. You can call size to get the count of how many items in that container. This size method in the vector class is also in arrays, is also in maps in all of them, is also in sets in all of them, is also in linked list in all of them. And other functions are also common between all of them. You're gonna have only a handful of functions specific for each container. Then I need you to know about stacks and queues. Now, stacks and queues are associative. They are not They are not sequential, so let's add it here. Stacks, queues. But linked list has its own chapter. Stacks and queues have their own chapter, so we are not gonna cover them today. Today, we aren't going to cover lists because they have their own chapter, and stacks and queues. There is a chapter called stacks and queues. So we are not going to cover them today, but it's good that you know about them. Actually, sorry, stacks and queues are, in fact, adapter classes, and they are sequential. Adapter classes means under the hood, you have what's called DQ, double-ended queue. Double-ended queue means imagine the container as, I know it has a chapter, but imagine the container is like a pipe. It's like a pipe. You add items from one end, and then you retrieve items from one end. That behavior is called LIFO. LIFO means last in, first out. FIFO, sorry. This container is FIFO. FIFO means first in, first out. So FIFO behavior means the first item that gets in will be pushed, would be the first item out. For example, if I add 3 integers, let's say, let's do 1, 5, and then 3. If I add 3 integers to this container, then I'm gonna first add 1. Then when I come to add the 5, the 1 is gonna move here, and then the 5 will take its place. Then when I add the integer 3, then 1 is gonna move here, 5 is gonna move here, and then 3 will be added. So if I want to access, I can only access one item at a time. I can't, like arrays. In arrays, you can provide the index and retrieve any item in the container. But with the stacks and the queues, you can only access one item at a time, which is at the tip of the container. You can only add one item at a time, and you can get one item at a time. You can't get any item from the stack. So when I ask my container to get me an item, it's gonna get me the 1 first. So the first item that went in was or becomes the first item to be out. Now this is the queue. Double-ended queue means you can add from both ends, and then you can add from both. You can add from both ends, and then you can get from both ends. Double-ended queue. The one you see in front of you is a queue. Double-ended queue means you can do this behavior from both sides. You have FIFO, you have LIFO, last in, first out, and then you have first in, first out. Stacks, on the other hand, are the LIFO. So if I go back here really quick, stacks are like a cylinder, closed from one end and open from one end. You add items from here, and then you get items from here. This behavior is LIFO, because if I want to add those, it's gonna look like this. So the last item that went in, which is the 3, would be the first item to get out. So last in, first out. When you have double-ended queues, you have FIFO behavior on both sides. So the double-ended queue is a sequential container, but this double-ended queue is used under the hood to provide you as a programmer a container called stacks and queues. So both stacks and the queues use double-ended queues. We're gonna cover them in details in that chapter and also linked list in details. So let's go back to the point where 75% of the functions are shared. So I'm gonna list some of the shared functions, and then we're gonna focus on the specific functions for each container. This specific chapter is basically more of knowledge base than practice for coding. Of course, without practicing, you're not going to learn. But this chapter is more for informing you what's out there. Unlike other chapters where we have like hands-on coding, like in classes, inheritance, etc., we basically code more than we write write information. But in this chapter, we have to just list and inform you what are the functions that are provided for you. Of course, whenever you want to use any of these containers, whether they are sequential or associative, you're going to have to include the library. For example, if I want to include vector, if I want to use a vector, I have to include the header. If I want to use a map, I have to include the map. If I want to use a set, I have to include the set. So let's go over each and every container and tell you more about it. We start by the array class. Now, perhaps this is the simplest container in the STL library. It's the array. You already know what an array is, and it has been like old since maybe before C++. However, C++ provided you the library that contains all the functions, so you don't have to redo all the work. So let me go ahead and include array. Array is the same exact container, just like you used to use traditional arrays. The only advantage that the object or the container from STL array, the only advantage is the size function. In order to create an array from that object, I can tell it I need an array. For example, int, I need 4 items of int. I'm going to call it my array. And then I'm going to give it some values, just like I do with my traditional array. So the only advantage here is my array has a size method. In traditional array, you say I want int 4, and 4 has to be like constant. And then you say my traditional array, and then you give it the number 1, 2, 3, 4. So this traditional array does not have, my traditional array does not have a size method. However, the object from that STL library has a size method. This is the only significant difference. Beside size, you have a list of functions. Now, out of these functions you're gonna see in front of you, those are the functions that 70% of them are shared. So let's go to table 17-5, which is page 1033. You're gonna see the array member functions. You have at method, back, begin, cbegin, cend. So those are all provided by you. Back will return a reference or an iterator to the last element in that container. Begin will return an iterator to the first item in that container. Cend will return constant iterator. So cbegin is constant begin, cend is constant begin. Then you have cr begin, means constant reverse begin. So if begin returns the first item, reverse begin returns the last item. And if end returns the last item, or not end, back. Back returns the last item. Reverse back returns the first item. Then you have end. End will point at the slot after the end, which is null, basically. So in my container, in order to find in STL containers, in order to find an item, you're gonna have your container, and it's gonna have, this is your container, not the memory. So if my container is like this, after my container, there is always a null terminator here. It can be continuous, it can be sequential, it can be associative. That's not our concern. My concern is this is begin. This item is back. This item is end. So when I call, for example, the find method, because every container has a find method. If I call find item, for example, 1, and 1 does not exist, that means the function went over the entire container, reached null, and it didn't find the item number 1, so it will return null. So whenever I'm trying to search my container, I always check if find equals my container dot end. That's how I find. So if my find method equals end means null, that means not found. It wasn't able to find. Otherwise, find will return an iterator to the item 1. So if the item 1 found, it will return an iterator to it, meaning, hey, this is 1. Here is an iterator of it. Otherwise, it will return null. So this is what I need you to focus or keep in mind. End is the item after the container, which is null. Back is the actual last item. Then we have empty, which returns Boolean, whether this container is empty or not. We have fill, front, max size, rbegin, rend, size, swap. Each function has its explanation next to it. Then they go to Iterator, the book. I'm going by the book. On the next page, they want to elaborate on iterators. So you have different types of iterators as well. Similar to containers, you have different type of containers. You also have different types of iterators. You have what is called forward iterator, You have bi-directional, you don't have backward. You have bi-directional iterator. Then you have random access. Then you have input, you have output. Forward iterator means it can only move forward. Plus plus with the plus plus operator, with operator plus plus. Meaning, if this is my container, a forward iterator can only go forward. I can't, if I am at point, for example, if I am at item number 1, I can't move back. I can only move forward. A bidirectional iterator, on the other hand, I can use the increment operator and also the decrement operator. So I can move forward, then I can move backward, then forward again, then backward. With random access, I can random access with an index, for example. Remember, with array, similar to the array, I can randomly jump on the items. I can access this item at this point, then this item at this point, then this item at this point, then this item, etc. Input and output, don't worry about them. Input and output are just for the streams, whether it's from screen or from a file or. It's an iterator that is used to read and write into data um, into or from an input device or a file. So how do I create an iterator? For example, I have my array. I can tell my program that I need first, the format is container type. What is the container type? Colon, and then the keyword iterator. Then the iterator name, of course. Iterator name goes here. It's like a variable name. So in my case here, I can say I need an array of int, for example, int 4, colon, iterator. Then I can call it my iterator. So this iterator behaves like a pointer. Remember how to dereference a pointer? How can I get the value that this pointer is pointing to? By dereferencing it with the asterisk. So I can say iterator with an asterisk end line. This will display random for now because I didn't assign any values to it. So now if I go ahead and display, it's going to display the size, which is 4, and then maybe null or junk value. I didn't assign any values to it. So yeah, saying, yeah, what are you trying to do? You can't dereference an uninitialized iterator. So what I can do is we go back here. This begin returns an iterator. This back returns an iterator. End returns an iterator. So I can tell my program this iterator equals my array dot begin, for example. So now this array, now this iterator, I mean, points to the beginning of my array. So if I dereference it, it's going to display 1. Here it is. Then I can, for example, say my iterator plus plus, then see out it again. Now it will display 2. So this as a default is bidirectional. I can increment and decrement, or I can specify forward iterator. So forward iterator. Where's my forward iterator? Does arrays don't have? So if I say it's an iterator and then I use my iterator negative, will it work? Is this bidirectional by default? So it is bidirectional. What if I want only forward? How come it doesn't have forward iterator? Interesting. Maybe arrays don't have it. Iterator. So this is the idea behind an iterator. It's a pointer or a reference or an object that points to an item from an STL container. This is an STL container, and this is a pointer to an item of that STL container. And this is how I get an iterator from a container object. I tell my container object, hey, give me an iterator to your begin. Give me an iterator to your back, for example. You do have a back. You don't have a back? Int. Oh, back gives me the value. Ah, I see. Oops, sorry. So this should display the last item. Okay, I see. So this back will return. So this back returns the value. If I need a reference to the end, I can use reverse begin. So just like I used begin earlier, I can use reverse begin, then this will become an iterator. So this will display 4 because I'm dereferencing reverse begin. So here it is 4. And the first 4 is for the size. Let's see what the book is showing next. The vector class. So we know the vector class. In order to use it, I need to include, and then I can tell it I need vector of, for example, ints. I'm gonna call it my vector. Then this container from the template library, STL, will provide me a bunch of methods that are 70% common and 30% specific. This specific container, my vector, is sequential in memory, means all the items in memory are in the same block of memory. And it provides me with constructor. For example, it provided me with this operator. It can also provide me with a constructor, fill constructor, copy constructor, meaning I can construct a container from another container. That's what it means by copy constructor. I can create a vector and tell it, hey, construct yourself based on another vector. Also, it provides me with a bunch of functions. Look at table 17-8, which is page 1041. I have assign, those are specific. Then I have at, shared or common, back, begin, common, capacity, C begin, C end, clear, CR begin, CR end. So most of those are shared. Capacity means how many items can this vector carry continuous in memory. The size can be 5, but it can carry 100 sequentially in memory. Once you reach that 100, then the entire container will be copied from that block of memory to a new block of memory that can carry more than 100. If I keep pushing, if the capacity is, for example, 100, and then I keep adding items and I reach the 100, in order to maintain the sequential property or the continuous slots in memory, the last time I push after 100, meaning I reached my capacity and I'm over my capacity, then that last push back to that vector will copy the entire vector from the existing block of memory to a new block of memory that has a bigger capacity. Then it has in place back, empty, end, erase, a front. So a lot of methods are common. Every method has its own explanation next to it. You have popback, which is the opposite of pushback. Popback will remove the item from the end of the vector. Pushback will add an item to the end of the vector. You have a resize method. So in arrays, you can't resize. An array has a fixed size, but with vectors, you can say, okay, my vector is 10, I need to resize it to 5. It's a method called resize. You have a swap. You can swap vectors. So you can call on your vector, you can say swap with another vector. So those items will go to the second vector, and then the second vector will have the item from this vector. Then, of course, it's showing you in the book, it's showing you how to create a vector, how to perform some of the tasks of vector. It's telling you that you can use int, you can use a string. You already know this, we already know that. It's a template class. It can carry any data type that we want. Using an iterator, for example, what was the format, if you remember? Container type, colon, iterator, and then iterator name. So if I want to follow this format, the container type is vector of ints, colon, iterator, and this iterator would be, I'm going to give it a name, my iterator. This iterator, at this point, I would like it to be, for example, dot begin. Now, if I dereference this iterator, it will show me the item. So my iterator. So the first one it should show me the it should show me the address. So 1, because begin is 1. I'm dereferencing that pointer. Insert, you can insert an item. You can tell it I need to insert an item between 1 and 2, for example, instead of push back. Of course, insert is a little expensive because vector is sequential in memory. Every time you insert, it needs to shift all the items on the right to one slot to the right because it needs to maintain continuity in the memory, right? If I have 1, 2, 3, 4, and I tell it I need to insert 2.5, then 4 should go here, 3 should go here, and then 2.5 comes here. So insert in vectors is expensive, and that's why they came up with associative vectors, associative containers, sorry. If your logic depends heavily on inserting, then you should not use a vector, because every time you insert, you need to, your container has to shift all the items. What if you have 1 million items? Every time you insert, you're shifting 500,000 items, for example. A lot of problems can be solved in programming. A lot of problems can be solved quicker if you use the right data structure. The containers are data structures. They struct data. So if you pick the right data structure, it's gonna solve the problem much quicker. Just like picking the right algorithm or sorting algorithm. Picking the right sorting algorithm based on your logic, based on how the data is structured, will solve the problem significantly quicker. Then they show you in vector, you can use your own data type. We already did this. I can create a class and then I can tell my program I want a vector of that class. For example, in the last homework, we had a vector of my struct. My struct is a user-defined user as me, as a programmer, is a programmer-defined data type. And I called the template class vector, and I told it I need to carry this, my defined data type. Then we go to map, multi-map, and ordered map. So a map is very interesting container. A map has this structure, black, this. So a map has key, value items. So I have value, and then I have a key. Every item in a map is this pair. So this would be the first item, then the second item would be this, the third item would be this, the fourth item would be this. This is index 0, for example, index 1, index 2, index 3. This is my container. Vertically this time. Usually I draw it horizontally. So if this is my container and these are the indexes, every item is a key value pair. Key value. Now in maps, just map, like map. So let me create it. When I say I need a map, for example, int string, my map. When I tell it I only need map, I don't specify if it's unordered or multi. That means the keys, so this is the data type for the key, and this is the data type for the value. Remember, every item is a pair. So here I'm telling it I need a map where the key is an integer and the value that the key maps to or points to is a string. I can choose whatever I want. I can choose any object. But you're going to have to overload some functions. Anyhow, in this case, this map as is not unordered and is not multi. Unordered means the keys are not sorted. Unordered maps means it's a container where keys are not sorted. So in my case, the keys are going to be sorted. Every time I add a pair, the map under the hood will sort my keys, meaning the item at the very beginning of my map is always the lowest key. And the item at the very end of my key of my map has the highest key. If my keys are 1, 10, 100, 1000, it doesn't matter what order I add them into the map. I can add the 1000 first, then the 10, then the 100. However, once I add all four, because it is an ordered map, it's not unordered map, then the keys will be sorted. The 10 will come first, the 100 will come here, then 1000, etc. They're gonna be sorted. The map doesn't control or maintain anything for the value. The values can be unordered, ordered, duplicated, whatever. This is not what controls the map. The keys are what control a map. Key, value. The values can be anything. They can all be equal to the same each other. But keys are what control the map. And the map is very fast to access an item. It doesn't iterate in order to access an item. Once you tell it, give me that, for example, index, it accesses right into that index and gets you the value, whether you have 10 items or 1 million items. So back to my point where I said, if you pick the right data structure, you might solve or you will solve the problem much quicker. If your logic depends on this behavior, then you better use a map because it's very fast. So back to my point, unordered means they aren't sorted. This, like this, how it's written, means sorted, because I can tell it I need unordered map. I need to include it. Unordered map. So unordered map means they aren't sorted. I don't care about sorting. Map means sorted. So unsorted keys, sorted keys. Deal? Now we come to multi. Keys and maps, in this map, the default one, the keys cannot be duplicated. If I tell it I need, for example, to add key equal 1, value equals Khalil or Khalil, and then I tell it again, add key equals 1, value equals Khalaf, it's not going to allow duplicated keys. It's not going to error. It will just override. So this one will set an item called, an item evaluates to key equal 1, value equal Khalil. On the next add, when it sees key equal 1, it will go and replace whatever the value of key 1. So key equal 1, okay, I have it. What's the value? Khalaf, okay, it's no longer Khalil, now it's Khalaf. In a map, you cannot have duplicates, no duplicates. Unsorted, no duplicated keys, no duplicated keys. However, if I specify that I need a multi-map, for example, I need multi-map unordered. Let's do one unordered multi-map. And this time it is int string my map. So this would be unsorted keys allows duplicates. On the other hand, I can tell it I need a multi-map, not a map. That means sorted keys multi-map, so allows duplicates. Deal. So these are the 4 different maps. We're gonna focus on the default one, meaning keys are sorted and no duplicates are allowed. So how do I add items to this map? I can say we have insert methods, just like vector, by the way. Look, in vector, you had default constructor, copy constructor. I'm looking at table 17-9, page 1055. The same table was in vector. But vector had a fill constructor. A map doesn't have a fill constructor, but they are common. So once you understand one of them, you can understand all of them. Now look at table 17-10. Everything you see is common between maps, sets, linked lists, stacks, queues, and vector. You have at, which takes a key similar to an index, begin, end, clear, count, cr begin, cr end, in place, empty, end, erase, etc. I can insert a pair, so I can use the function insert to insert one key, so that insert, and this takes a pair. Look, std pair const int string, so it takes a pair. If you want to insert into your map, you need a pair, so I'm going to tell it std pair. This pair would be key equals 1, name is value is Khalil. What is it? Argument list of class template SV is missing. Make pair. So make pair this and that. Now we can get rid of this. So it's a function that returns a pair. So see, it returns a pair and it's called make pair, and it takes a bunch of values. It takes an integer, then constant char as an array. In this case, it's taking 7 because those are 7 characters. So make pair, I just inserted one, or I can do my map at 2. So at this equals Khalaf. This is another way. Now, if 2 exists, it will replace it. If 2 doesn't exist, then it will add it and add its value. Another way is my map at, well, it's the same basically. It's the same, yeah. These are 2 different ways. For example, a good problem to use maps, for example, counting how many, for example, if I say you have a sentence from the screen, I need you to count, I need you to display how many A's are in this screens, how many B, how many C's, how many D's. If a character is not found, don't display anything. The best way, the worst way to solve this problem is by declaring 26 integers, 1 integer for each character in the alphabet. So an integer called A's count, then B's count, C's count. Then you're going to iterate your sentence. If it's an A, increment A. Else if B, increment B. Else if C, increment C. So you're going to have 26 if-else statements beside the 26 variables. And all those lines are within a loop. That loop is going to iterate the sentence from the beginning to the end. Once you're done populating your integers or counts, then you're going to go another loop, and then you're going to display. You're going to have 26 if-else statements. If A's count is not 0, display. If B's count is not 0, display. If C's count is not 0, display, so on and so forth. So that would be the worst approach. The best approach, the smartest approach, is using a map. in that case, my map would be what? Since alphabets are unique, there are no duplicates. So I'm gonna use the alphabet as the key, and then the value as their count. So for example, I'm gonna say I need a map that has key as a char and int as value. Then I'm gonna say, okay, get line from the cn into my str, my string, and then I'm gonna tell it string my str. Right, so I got a sentence from the user. Then I'm gonna iterate equals 0, I less than my str dots whatever size is I plus plus. On each iteration, I'm gonna check if I have that character already as a key, then increment it. Otherwise, add it and set its value to 1, right? If my map is empty, the first character will not exist. So I'm gonna add the key and the value would be 1 because it occurred once. I just hit it. Then on the next character, the same. Does this exist? If yes, increment its value. If no, add it and set its value to 1. I can do this routine using only one line, which is my map at this character, plus plus. So let's break this down just so you know. Remember from previous example, this operator takes a key. And if the key exists, now in this case, if the key exists, it will increment its value. If its value, meaning the value, not the key, the value. If the key, for example, A exists, the operator plus plus will increment its value. It's not gonna make it B, it's gonna stay A, but plus plus will increment the value. So if A doesn't exist, it will add it to the map with a value equals to 0, then this operator will come and increment that 0 to be 1. Then finally, I can just iterate my map using an iterator. I can iterate it using an iterator. So I can say, for example, I need a map. Map char with int iterator, my iterator. I'm gonna call it L begin. This L begin equals what? Equals my map begin dot begin. Then I'm gonna say for, I already declared it, while L begin is not equal to my, let's scroll down, while L begin is not equal to my map, dot end, means as long as I didn't reach the end, and my increment or my moving condition is L begin plus plus. On each iteration, I'm gonna say cout key L begin dot iterator. I mean, not L begin, since it's an iterator, so pointer. First is the key. You see, I have a key and I have first and second. First is the key. Then I'm gonna say tab value or count. So I'm gonna say here letter count L begin dot not dot arrow second and L. So if I run it now, I'm gonna say hello from the other side. So do I have any A's? I don't have any A's. Do I have any B's? I don't have any B's. C, no. D, no. So A, B, C, D, E, I have 1, 2, 3, 4, so on, so forth. So enter, boom, enter. So notice it counted the space as a character. I have 4 spaces, 1, 2, 3, 4. It counted the exclamation mark as a character. I only have 1. Letter F, it counted 1, only 1. H is 1, da 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 da. It also took into consideration that small letters are bigger, are different than capital letter. For example, do I have anything in common? H, O, O. So letter O, small letter 2 times, letter O 1 time. I can change this. I can say only add small small letters. So if I go here, I can say grab this one to lower, to lower. Now it will only add it whatever it is. If it's a big letter O or small letter O, it's gonna count them the same. So identify not to lower. How come it's not? STD lower, to lower. Okay, here it is. To lower. Run again. Hello from the other side. So now O are 3 and no capital letters because every encounter has been treated as a small letter. So pretty cool. That's the right approach to this kind of problem. So moving on. Of course, you can add your own objects into your map. I'm assuming next is the set. Okay, they speak about unordered map. We already mentioned that. They don't notice how they were sorted. Oh, this is the previous one. Look, because it was I didn't declare it as unordered map, then the keys when I iterated, so I'm gonna show you. Hello from the other side. When I said give me begin and then iterate from begin to end, look how begin is the smallest value. D, E, F, H, so they are sorted. If I tell it I don't want sort, so meaning unordered map, then this becomes unordered map 2, and I run again. Now it's not gonna display them as assorted. Hello from the other side. It's gonna display them the same way it approached them. H first, E, then L, then O's, etc. Enter, enter. So H, oh, interesting. Why M before? They are still not sorted. But why M is before L or before E even? I'm curious. Go here, run. Hello from the other side. So my string at I is H. Okay. Go. So now size is 1. Now it's E, go. Now it's 2, so H, E, okay. Now it's L, go. H, E, L, go. So H, oh, why? Okay, well, I can look at it later. If you're curious too, you can look at it later. Multi-map allows duplicate keys, so I can add without overriding. Then finally, we come to set. A set is basically uniqueness of values. So I'm going to remove this. A set is basically a container of items, not pairs, just items. For example, if I have a set of integers, let's say I have this set of integers and I have this pool of values. I have 1, 2, 3, 1, 5, 7, 6, 2, 3, 7. So I'm going to start adding to this set. Set cares about uniqueness. So I'm going to use a blue. Add 1. Okay, I added 1. Add 2. Okay, I added 2. Add 3. Okay, I added 3. Add 1. Well, I have 1. Okay, do nothing. Add 5. Okay. Add 6. Okay. Add 7. Okay. Add 2. Well, I have 2. Okay, then do nothing. Add 3. I have 3. Do nothing. Add 7. I had 7. Do nothing. So if I add this pool to a set of integers, this would be my container. It would be this set of values. It's like in mathematics. A set is like a set of values. 1, 2, 3. No matter how many times it encountered those values, this is the set of values. It's like an alphabet. The set of letters is 26. Whether you can write a book of 1,000 pages using that same set of alphabet. Using the same set, 26, you can write 1,000 pages a book. So this is basically the simple idea of a set. Then you have, similar to maps, you have unordered set and you have multi-set. Multi-set allows duplicates. So if you use an unordered or sorry, multi-set, then you're gonna lose that feature of having uniqueness, of course, but you're gonna still gain fast and quickness because the set is fast to access. It takes, if you're interested in algorithm or theory or algorithm design, it takes O1 to access an item. O notation, it's called O notation, means how complicated it is to access an item. 1 means constant, meaning it takes constant time to access an item no matter what the size is. Whether the size is 0 or n, it always takes constant complexity to access one item. Maps as well, O1. For example, the complexity of this loop, how complicated it is. Complicated means time, processing power, etc. Can you guess? If we were in class, I would give you like 30 seconds to guess how complicated it is in terms of O notation. The O notation here is, since it's going from 0 to size, means it depends on the size. Meaning, if it depends on the size, then it's not constant time. Because if the size is small, then it's small time. If the size is big, then it's big time. It's a lot of time. So since this loop depends on the size, then the complexity is O(n), means the size. That's the notation. The complexity of this loop is O(n). The complexity of accessing an item in a set is O1. if you get into an interview in an advanced session and they ask you to write code, they're gonna ask you questions like this. They're gonna, okay, write me a solution. You have this problem, write me the code, right? And you go ahead and write the code. And then they're gonna open the code and start asking you, what do you think is the complexity of this code? How much complicated do you think it is? Since it, for example, if I'm always iterating 0 to 10, then the complexity is 10 because it's constant. I don't count on the size. It's always 10. Yeah, so let's see what else. On page 17, 13, this is the table for the methods provided to you by the set. It's equivalent to map and vector, not equivalent, I mean, they share like 80%. There are only specific methods to a map because it has pairs. There are only specific methods to vector, which is pushback, pop back. For a set, let's see what's specific about it. I don't see anything specific in this table, specific to a set. All those are shared or are common. For example, let's say I ask you to read a sentence from the user and tell me all the alphabets he used in that sentence, right? So I don't care what, for now, we don't care if it's ordered or unordered. The best approach is, well, let's speak about the worst approach. The worst approach is adding a Boolean, 26 Booleans for the 26 alphabets. A exists, B exists, C exists, 26 Booleans. Then every time I iterate the sentence, then I add 26 if-else statements. I say, okay, if the character is A, then A exists equal true. If the character is B, B exists equal true. If the character is C, C exists equals true, 26. Then in order to display, I have a loop for 26 because I have 26 alphabets. Go from the first Boolean to the last Boolean. If that Boolean is true, display it. Else, don't do anything. That would be the worst because it's a lot of code. The best solution is using a set, because back to this example, I'm going to have a pool of characters, and then I'm going to just dump them in a set, and the set will manage uniqueness for me. So I can say I need, let's take it off. So I'm going to say I have, actually, we need the get line and that. So here is string, get a string from the user. Then I'm going to say, okay, I need a set of char, my set. Then I'm going to say, okay, iterate. Of course, I can use any type of loop. This is the type of loop I'm using has nothing to do with how fast the program is. It's just preference. For me, I'm just going to use this. I can use for each, range-based, etc. Int I, as long as my str.size. In other words, no matter how the code looks like, it's going to be fast. I++. Of course, it's better to look nicer. So for the entire size on each character, my set dot insert. Do I want to do insert? Fine, insert mstr, because it is sets are associative, so I don't care about insert. Okay, my str at I, semicolon, and that's it. If my str at I exists, then the set is gonna manage it for me. I don't have to manage it. The set is just gonna ignore it. So Now I can iterate again. I equals 0. I, at this time, my set dot size. How many characters? Are they 5 characters, 10 characters, whatever alphabet I have? For the size, I++, and on each iteration, I need to see out my set at I with a space. At, fine. Dot at. Oh, interesting. Let's do iterator then. Then let's do, I need an auto iterator equals my set dot begin. Then I'm gonna say this has been initialized, or I can actually put it here. So X V here, and then I can say as long as iterator is not my set dot end, is not the null, and then the increment condition, my or iterator. Now on each iteration, I need to dereference this iterator. Go. So again, hello from the other side. Then it's gonna tell me, okay, you used this, and that's it. Let's do it to lower. So C out and L. And then here, insert to lower. Now it's gonna only show me unique. So hello from the other side. I used space character, this, this, and that's it. So this sentence was built using this set of characters or set of alphabets. We're gonna stop here. There's one more topic about algorithms, but basically they speak about sorting, and we already covered sorting. Sorting as in sorting a container. We already did the selection sort, bubble sort. Yeah, okay, that's it. So let me know if you need any help with this, or if you need help with the project or with the homework.